Hello. In this video, I'd like to review some of the tools that archaeologists have used, mainly after borrowing them from geographers, to analyze settlement patterns of the past. These include ones they've attempted to apply to the identification of site hierarchies, relationships of settlements to environmental zones, and even ancient political boundaries. I'll emphasize not only the usefulness of some of these methods, but also their problems and limitations, which are sometimes severe enough to explain why they do not see more use than they currently do in archaeology. Many of them fall into a group that we might loosely call point pattern analyses. From the mid-19th century onwards, archaeologists have been interested in the spatial distribution of sites on landscapes. They often treated settlements and other kinds of sites somewhat like points on the landscape. This has allowed them to look for patterns in the distribution of those sites, especially with respect to economic resources, such as flint outcrops, metallic ores, and arable land. But it also allowed archaeologists to study the relationships of sites to one another. Almost 2 centuries ago, Johann Heinrich von Thunen proposed a theory called central place theory about the economic zonation around a city. According to this theory, the zones are concentric, with the most intensive land use and highest land values and rents in the inner zone, extensive agriculture in the zone outside that, and low-intensity land uses, such as forestry and pasture, in the outermost zones. This theory is the basis of much later ones, such as site catchment analysis in the 1970s, but also the inspiration for the theories of the geographer Walter Christaller and economist August Lusch. They studied the spatial relationships among cities and the towns in their territories, noting that in certain idealized conditions, these tended to be arranged in hexagonal patterns. In addition, the towns themselves were also surrounded by hexagonal patterns of smaller settlements. They identified several versions of these patterns that were influenced by market principles, transportation needs, and the number of levels in the hierarchy. Lusch also demonstrated how various departures from the idealized flat plane could cause distortions to the ideal Christalleran settlement lattice. Even when they're somewhat distorted, Christalleran settlement lattices have very even distributions of the settlements in them. The distances between each settlement and its nearest neighbor are similar and relatively large. Consequently, examining these distances gives us some insight into the structure of the settlement pattern. Nearest-neighbor analysis is a simple method for examining this structure. Whenever settlements occur in clusters, those nearest neighbor distances are relatively small. In random distributions, the average distance between each point and its nearest neighbor is between the average for an even distribution and that for a clustered one. Nearest neighbor analysis involves measuring all of these distances and then averaging them. One of the issues of concern when we do nearest neighbor analysis is called edge effects. If there are sites lying just outside the edges of our study region, failure to include those sites will result in a biased estimate of the average distance to nearest neighbor. Consequently, it's a good idea to have something like a buffer zone around the edges of your study area, and then use sites in the buffer zone as nearest neighbors to ones in the more central area when appropriate. The value of the nearest neighbor statistic depends on 3 things: the average distance to nearest neighbor, the area of the study region, and the number of points in that region. Its calculation is a simple ratio, with the average distance to nearest neighbor in the numerator of the ratio. In the denominator, we first take the total area and divide it by the number of points, then take the square root, and then multiply by 0.5. If the result is close to 1, then we have a random distribution. If it's a low value, then the distribution is clustered. And if it's high, up to a maximum that's a little bit over 2, then it's an even distribution. While geographers have to worry about edge effects, archaeologists have another source of concern: the chronology of the sites in the settlement system. Typically, and especially for survey data, the sites in the system are of uncertain date, and consequently, we can't be sure that all the sites are contemporary with one another. In the example shown here, if all the red dots represent settlements that were occupied at the same time, and the white dots are ones that were occupied in different periods, then including those white dots in the analysis would tend to underrepresent the average distance to nearest neighbor, leading to a biased nearest neighbor statistic. If we knew that those earlier or later sites did not belong to the same settlement system, we could exclude them from analysis and result in a more accurate nearest neighbor statistic. One aspect of complex settlement systems, such as the idealized Christalleran Settlement Lattice, is that the sites have hierarchies. Large sites may be surrounded by smaller sites, and those in turn surrounded by sites that are smaller still. In some cases, there are hierarchical relationships among those sites of different size. The differences among sites at different levels in the hierarchy may be functional. For example, the largest site could be a base camp, while the smaller ones represent different kinds of special activities or different seasons of occupation. In the case of Chris Thaler's urbanized landscapes, the largest site is a city, surrounded by smaller towns, which in turn are surrounded by villages. In this case, the relationships could be administrative, with occupants of the city governing the people in the towns. And some of those relationships are usually economic, with people in the villages and towns providing food and other resources, and perhaps taxes, to the city. The city might also provide some services to the towns and villages, such as markets, post offices, and places of worship. One of the first steps in archaeologists' attempts to identify site hierarchies is usually to draw a histogram of site size. In the results of a typical archaeological survey, most of the sites are likely to be quite small. There may be one or two extremely large sites, and a few sites that are just a little bit smaller. However, the presence of a bimodal or trimodal distribution by site size is not itself sufficient to show that there's a site hierarchy. Size variations can occur for a wide variety of reasons, and they're not able to demonstrate whether or not there were any relationships among the sites of different size. Consequently, we need to supplement these results with other methods. One method allows us to estimate the boundaries between the larger sites in a region. We can then see whether smaller sites happen to be distributed within those boundaries in a way that's consistent with some version of site hierarchy. The shapes that result from this method are called Feasin polygons, and the simplest version of Feasin polygons are unweighted ones. In unweighted Feasin polygons, the boundaries are exactly halfway between each pair of settlements. This treats all of the central sites equally, irrespective of their size. However, it's a reasonable assumption that larger sites may be more influential, or may extract resources over a larger territory. To account for these differences, one option is to use weighted Feasin polygons. Instead of placing the boundary exactly halfway between two neighboring settlements, we use the ratio of the sizes of the two settlements to one another to decide on the placement of the boundary. However, for now, let's demonstrate the construction of Feasin polygons using the simpler method. For a pair of sites like these two, we begin by drawing a line segment that joins them. We then find the halfway point along that line segment and draw another line segment that's perpendicular to it at that point. You can do this by using a ruler and a right-angled triangle. You can draw Feasin polygons using tools no more sophisticated than a ruler. However, a very useful tool to use if you're drawing unweighted Feasin polygons is a draftsman's compass, because it really simplifies the process, and I'm going to show you how that works. With this method, you don't actually need to draw a line segment between the two settlements. However, I'll leave that on there just for reference. We begin by sticking the point of the compass in the middle of one of the dots and then drawing an arc. And then do the same with the other dot so that the arcs cross. We also do that with two arcs at the bottom here. Next, we use a ruler to draw a line segment that passes through the two places where the arcs cross. This line segment is equidistant from the 2 points, and consequently is the boundary for unweighted Feasin polygons. The next step is simply to erase our unwanted pencil marks, leaving just the boundary. To make full Feasin polygons, we have to repeat this process for every pair of adjacent points. For this demonstration, I'll use the first method and begin by drawing line segments between adjacent pairs of points. We then draw perpendicular line segments at the halfway points between each adjacent pair. To finish up, we erase any unneeded line segments as well as the overlaps between line segments at the corners. The final result is our finished set of Feasin polygons, and we may also want to erase those initial line segments that went between adjacent pairs of points. In the final outcome, notice the edge effects. Because the outer settlements are not constrained on their outer edges, we don't know where their outer boundaries lie, and we get an exaggerated idea of their territorial area. Another method that archaeologists have borrowed from geographers in their attempt to identify settlement hierarchies is called rank size analysis. It's based on the observation, usually called Zipf's law, that there's a power relationship between the sizes of sites in the hierarchy. For example, the top-ranked site might have twice the population of the second-ranked site, and 3 times the population of the third-ranked site, and so on. The usual way to analyze this is with rank size graphs, typically with a logarithmic scale on both axes. When we plot site sizes against site rank in this way, a log normal distribution would be one that results in a straight line. Real size distributions are likely to depart from this straight line, either being convex, when the several top-ranked sites are all of closely similar size, or concave, when the largest site is vastly bigger than the second and third-ranked sites. Archaeologists typically call this last kind of distribution a primate distribution, because it seems to occur among some of the earliest urban landscapes. Because real distributions vary considerably between the extremes of convex and primate shown here, archaeologists who use this method like to have some statistical measure of how much the distribution departs from the log normal model. One approach that some archaeologists have used is the Kolmogorov-Smirnov test. It's based on the statistic d, which is the maximum distance between the curve and the log normal line. A better approach is based on the entire area between the log normal line and the curve. You'll find sources for more information on this method in the bibliography at the end of the video. No matter which statistical method we use to analyze rank size curves, we need to be aware of some of the problems when we use them with archaeological data. One problem is a sampling one, in that our sample probably doesn't include all of the sites. Some sites may be destroyed or deeply buried, and surveys are imperfect so that they omit some sites, and especially small sites. Because of this last issue, you'll notice that a lot of rank size graphs have a steep tail at the right end of the distribution. This is a telltale sign that a lot of small sites are missing. But there are other problems too. Once again, there can be problems with edge effects, in that we don't really know the boundaries of the settlement system, and we may have inadvertently included some large sites that actually belong to a neighboring settlement system. And once again, we have to worry about contemporaneity. Our rank size graph could be including sites that weren't actually in existence at the same time. In the equation that describes Zipf's law, the denominator has rank raised to the power of k, and in the classic Zipf case, k is equal to 1, so that the second-ranked site is half the size of the first-ranked site, and so on. But more generally, k does not have to equal 1. In fact, that exponent does not even have to be a whole number. And this makes Zipf's law an example of a fractal relationship. The fact that some rank size distributions can have fractal properties reminds us that fractals might be relevant to other aspects of settlement patterns as well. You might be familiar with fractals because of some of the startling images that are associated with them, such as Mandelbrot sets. But more generally, fractals are something that results from simple deterministic processes that create patterns that exhibit self-similarity at different scales. Fractals are a feature of complex dynamical systems, as found in what's popularly known as chaos theory. Lots of things in both nature and culture have fractal properties. For example, a jagged coastline has infinite length and appears very similar in shape as we change the scale, right down to the point where the water touches the edges of pebbles and grains of sand on the edge of the beach. The branching of plants and river systems have fractal properties, as do the fluctuations in stock market indices. So it's not very surprising that settlement patterns also have fractal properties. In fact, we can measure the fractal dimension of a settlement system by using the box counting method. We begin by imposing a grid of large boxes over the map of the area, count how many squares have at least one site in them, and then subdivide the squares into smaller and smaller squares, at each stage counting how many squares contain sites. In this case, I began with squares that were 16 units on a side, and then 8, and then 4, and then 2, and then 1. It doesn't matter what the units are, because fractals are scale-free. Once we have our data, with S being the size of the boxes, A being the number of boxes that contain sites, we can calculate the logarithms of those two values. When we then plot a graph showing the relationship between those two logarithms, we typically get a straight line. We can find this line either by a regression analysis or we can estimate it by eye. The next step is to find the slope of the line, which we can get by dividing the rise by the run. The rise is negative because the line is actually going down to the right, and here it's minus 0.85, while the run is 0.6. The fractal dimension is just the negative of the ratio of these two values, which in this case is 1.42. Note that this indicates that the settlement pattern is neither one-dimensional nor two-dimensional, but actually 1.4-dimensional, indicating that the settlement pattern is somewhere in between linear and grid-like, since lines are one-dimensional. In this case, the fact that most of the sites are arranged along rivers and canals probably contributes to it being closer to a linear distribution than to a grid-like one. All of the methods I've discussed involve certain kinds of assumptions that aren't always supportable and are subject to various kinds of error, some of which I've already mentioned. Some of these are ones that both geographers and archaeologists need to worry about, and others are more specific to archaeology. One of the specifically archaeological problems is chronology. In archaeology, we can't always be sure that all of the sites we're including in our study were occupied or used simultaneously. As I've already noted, this can have negative impact on the results of nearest-neighbor analysis, construction of Feasin polygons, and rank size analysis. Even interpretation of site hierarchies could suffer if it turns out that the smaller sites in the hierarchy were actually occupied earlier than the large sites. Both geographers and archaeologists need to worry about edge effects, and the main concern is to ensure that we haven't accidentally omitted sites outside our study area that could have impact on our results. Such omissions can have particularly negative impacts on nearest-neighbor analysis and Feasin polygons. But sometimes archaeologists also have to concern themselves with whether or not they have accidentally included some sites that really don't belong to the same settlement system. Including large sites that don't belong can have particularly large impacts on rank size analysis and studies of site hierarchy. Sampling effects constitute yet another problem, and most of the time it's a problem of missing data. Sites can be missing because they've become destroyed or deeply buried over time, or because they're very difficult to find. They can also be missing just because survey was incomplete or not very thorough. Such omissions can have a particularly bad effect on nearest-neighbor analysis, Feasin polygons, and rank size analysis. Fractal analysis may have an advantage here in that its characteristic of self-similarity at different scales makes it possible for us to base the fractal dimension on a relatively small sample, as long as it covers a fairly contiguous large area. However, the box counting method would still be vulnerable to any missing sites within the sampled area. After I've described the many problems archaeologists can anticipate with most applications of these point pattern methods to archaeology, you might wonder why I'm talking about them at all. However, just because there are problems in a wide variety of contexts does not mean that they are never useful at all. In cases where we have thorough surveys, geoarchaeological evidence, and good control over chronology, some of these methods can still be quite informative. In some cases, in fact, they're the only options we have if we're to understand how different kinds of sites in different circumstances in their landscapes were interrelated. If you'd like to investigate other aspects of these methods, please have a look at the references I've listed at the end of this video. And if you'd like to be updated as I release new videos, please click on the subscribe button down below. Thank you, and stay safe.